Hello everyone, my name is Mai, a third-year student of PhD course in Hanawa Labo. Now I represent an article published on pharmaceuticals. The keywords are curcumin, solid dispersion, hydroxyropyl cellulose, sodium dodecyl sulfate, and bone milling. The poor aqueous solubility of drug causes low permeability through cell membranes, reduction of absorption, and thus decrease the bioavailability. An API can exist in crystalline and amorphous form, whose solubility is up to 1,000-fold higher than crystalline form. Amorphous substances can be classified into pure drug and solid dispersion. Components of an SD are an API, polymer, or a mixture of polymer and surfactant. To avoid the waste of resources, design of experiment DOE is used. It can determine the relationship among factors, optimize resources, reveal problems, and resolve them. Furthermore, the DOE provides valuable information, allowing for validation before industrial manufacturing. In this study, we focus on curcumin and as a model of a poorly water-soluble API. Curcumin has been used in accelerating the wound healing. Hydroxyropyl cellulose (HPC) is used in SD formation to improve drug solubility. Sodium dodecyl sulfate (SDS) is a surfactant used to improve wettability, solubility, and dissolution rate of APIs. For prolonged contact with human skin, the SDS should not exceed 1% to avoid irritation. This is the preparation process of curcumin solid dispersion with 6 levels of HPC, 2 levels of SDS, and 5 levels of grinding time. The GMs were characterized using PXRD, FDIR, DSC, dissolution, and stability study. The conditions are shown on the screen. The stability study was done only for 60-minute GM containing curcumin, 90% HPC, and SDS. From the dissolution data, 5 factors of dissolution efficiency were calculated. The 5th factor consists of difference factor F1 and similarity factor F2. If F1 is lower than 15 and F2 is higher than 50, there is a similarity of the dissolution profiles of the reference and test samples. In this study, we consider the enhancement in dissolution rate of curcumin when forming curcumin solid dispersion. So we refer this similarity or F1 is higher than 15 and F2 is lower than 50. Dissolution efficiency is the blue area in the figure. Figure A and Figure B show the crystalline nature of curcumin, and there were reduction in the intensity of characteristic peaks of curcumin when the amount of HPC and the grinding time increased. In Figure C, some peaks were observed at 17 and 25 degrees for 15 and 30-minute GM, but they will disappear in 45 and 60-minute GMs. In Figure A, the red arrow shows peak of ethyl group, and the black arrow shows peak of acarbonyl group. There were increase in peak intensity at these 2 peaks. Because curcumin exists as ketoenol in solid state, it is considered that the hydrogen bond was formed between curcumin and curcumin. Let's see Figure B. As the amount of HPC in mixture increased up to 50%, the variation of this peak was also observed. In addition to curcumin and curcumin hydrogen bond, the hydrogen bond between curcumin and HPC were coexisted, particularly in GMs containing over 75% HPC. Figure C. 2 new peaks were observed and became more intensive when the grinding time increased. This suggests that the drug was well dispersed in the HPC and the only hydrogen bond between curcumin and HPC was formed. The presence of SDS did not influence the FTIR spectra of these GMs figure D because of its small amount. Figure A shows the vesicles of brown curcumin crystal, which express endothermic peaks at about 190 degrees Celsius due to their melting points. However, exothermic peaks at about 80 degrees Celsius indicated the recrystallization of curcumin. The grinding method transformed curcumin from crystalline to amorphous phase. The recrystallization peaks could be seen in GMs containing up to 50% HPC in figure B, but disappear in GMs containing 75% HPC in figure C. In case of tertiary GMs figure D, the presence of SDS raised the right shoulder and unstabilized the curcumin melting peaks. However, the recrystallization phenomenon could still be observed. Figure A shows dissolution profiles of brown curcumin crystal. As grinding time increased, the dissolution rate was enhanced because curcumin was partly transformed into an amorphous phase. Presence of HPC and SDS in mixture increased the dissolution rate of curcumin due to the hydrophilicity of HPC and the surfactant characteristic of SDS. The crystalline dissolution rate of curcumin was observed in 120 minute GMs containing 90% HPC and SDS. On F1 higher than 15, but F2 smaller than 50 was only observed in 4 GMs, namely 60-minute GMs containing 90% of HPC, as well as 30, 45, and 60-minute GMs containing 90% HPC and SDS. The presence of SDS reduced the grinding time from 60 to 30 minutes to develop an SD, which significantly increased the dissolution rate of curcumin. The DE was in the range 0.4 and 24 and was submitted into DOE as an output data. In the half-normal plot, HPC grinding time and presence of SDS are shown on the right-hand side of the red line, referring to their positive effects on the response. The distances to the red line indicated that the influence of HPC was much higher than that of grinding time and presence of SDS. The model p-value less than 0.05 shows significance. The peaks, area patterns, and dissolution profiles as stored conditions are recorded. The halo patterns of sample were stable up to 30 days in both conditions. However, curcumin characteristic peaks appear in sample after 60 days of storing. HPC may have protected the rock from crystallization for up to 30 days. In conclusion, in this study, the 60-minute GM containing 90% HPC significantly increased the curcumin solubility. Presence of SDS in GMs containing 90% HPC reduced the grinding time from 60 to 30 minutes in forming an SD, which significantly increased the rock dissolution rate. This amorphous state was stable for 30 days when stored in 40 degrees Celsius, relative humidity 75%. That's all. Thank you for your listening.